Welcome all. Today we have Professor Valentin Troll, who did originally from Germany, but he did his undergraduate in Britain at St. Andrews, then went back to Germany for PhD at GMR Institute, then has been lecturing several years at Trinity College in Dublin, and now since 2008 he is in Uppsala University, where he's working mostly on volcanic magmatic processes, and he's been working a lot on several active volcanoes, for example, the Iceland eruption from last year, but also the La Palma eruption from last year, and that is what he will be talking about.
Thank you very much. I hope you can hear me. I've been mic'd up. I'm not sure it's working, but it seems to be okay. So thank you very much for the invitation. It's a great pleasure being here. And as Froukje just said, I work on active volcanoes, and that's what I do with all aspects. And last year was certainly in Europe a very spectacular year. We had eruptions in Italy in Etna, we had eruptions in Iceland on the Reykjanes Peninsula, and we had eruptions on La Palma. And in the Canary Islands, which is an intra-plate volcanic system, it actually has some similarities to the old volcanic systems here in Saudi Arabia. So this is why there is a geological link, and this is why this has a little bit of a relevance for the local geology here as well. So this is special on La Palma because the last eruption on La Palma was 50 years ago. I was only half a year of age. And the next eruption on La Palma might be in another 50 years. So for me, this is a once-in-a-lifetime chance to see an active volcano on La Palma in the Canary Islands. And this is what I want to talk about today. So a quick introduction to the Canary Islands. People call it the European Hawaii, so it's very nice. It's a tourist destination, and it's a volcanic archipelago. It has 7 main islands, and they are within the Atlantic plate, close to a rift system in the mid-Atlantic. So this is geologically not dissimilar to some of the situation here. And the archipelago stretches from about 100 kilometers close to Africa to about 500 kilometers west of Africa. All islands are volcanic in origin, and there's a few former islands that have sunken below the sea. And let's see, here's the pointer. So this is the active islands, and then there's a few islands that are so deeply eroded that they're no longer visible above the water level, and they are even older. So there's an age progression. There's a chain, if you will, of islands, a bit like Hawaii, and the youngest islands are here in the west of the archipelago, and they go older towards the east, and most of the volcanic eruptions are therefore here, where young islands are in the west of the island chain. So the erosion pattern of the islands, they reflect the age, and here in the eastern part, we have deeply eroded islands, very flat, very desert-like. And here in the west, they're more steep. And the biggest island and the tallest island is Tenerife with Teide volcano, the highest peak of Spain, 3,700 meters. And geologically, we have to assume that Teide will now be drawn down by erosion. It will get smaller and smaller with time, while the islands here in the west, they will actually start to grow. So La Palma and El Hierro, these are islands that will still have a lot of history in front of them. So the situation looks a bit like that. We have a rotating plate, and underneath that rotating plate, we have a fixed anomaly in the mantle that brings up hot material. And this fixed anomaly, hopefully the video works here. Let's see. This fixed anomaly that's producing volcanoes, and the moving plate is then producing an island chain. So the mantle anomaly underneath, the hotspot as we call it, is stationary, and the plate moves very slow at about 2 centimeters a year. That's about the speed with which your fingernail grows, and it's producing over geological time a chain of islands. And the most recent volcanic activity is focused here in La Palma and the island of El Hierro on the western edge of this island chain. Now, the geology of La Palma, here's an island map of La Palma. We have the old volcanic shield up here, the Taburiente volcano as it's called, and we have a younger ridge, the Cumbre Vieja ridge, and most of the volcanic activity, the recent volcanic activity, happens along this ridge. This old shield volcano is extinct by now. It's dormant, there's no activity, and all the historical eruptions happened along this ridge. So the old Cumbre, the Nueva, is the part in between here that connects the very old Taburiente volcano with the Cumbre Vieja ridge. And the ridge continues submarine, so there's new little volcanoes growing under the water as well. And this is now focusing in onto the ridge. So here we have a little area that we are looking at, and there we have a number of historical eruptions. There was eruptions in 1585, 1712, 1677, and 1646, etc., etc. And then there was one in 1949, 1971, and now in 2021. So this is the most recent one. And all of these historical eruptions, they happened along this ridge, the Cumbre Vieja ridge. Here's a photo from the 1949 eruption. Here's one from the 1971 eruption. That's also from the 1971 eruption. And the latest eruption happened here in red, while the older ones are marked with this orange-brown color on this map. So here's a list of all the historical eruptions in the archipelago, and we don't have to go into details, but the first eruption was actually observed by Christopher Columbus on his way to America. There's an entry in his logbook that he saw a volcanic eruption, and it proved to be true. And if you count, then you'll find that 50% of all the volcanic eruptions in the archipelago happen on this one island, La Palma. And this makes it the volcanically most active island in the entire island chain. So here, this is, oops, let's go back one. This is some impressions when the eruption happened. You could actually see it from the air, of course. So here is us approaching it from with an airplane, and here you see the eruption piercing through the clouds. And it says everywhere on the airport, on the ferries, that there is volcanic alert, and you're not supposed to go there. You're not supposed to drive anywhere near it because, well, there was lava and heavy ashfall. And these are the key problems we will discuss during the rest of the talk, because they were quite devastating to the island economy and to the population there. So here's a quick summary, a quick rundown of the events. So there was earthquake activity that was stronger than usual for the last few years already. So this was at a depth of about 2 to 30 kilometers. And on 11th of September last year, seismic swarms were detected. And they were even stronger. And during the following days, it appeared that the earthquake intensity marked here in red was getting stronger and stronger. And there was a lot of seismic earthquake activity at 8 to 10 kilometers depth. And then there was ground deformation. The ground was starting to swell up, something like 20 centimeters beyond normal. And then, strangely enough, there was a decrease in seismicity. It started to calm down, just to reawaken 2 days later. And then the eruption started at 2 o'clock on September 19th. And it was initially very explosive, and it started to open a crack of about 500-meter length. The good news was it happened in an area where there was nobody living. So initially, the opening of the crack and the initial explosion didn't cause any harm to any people living there. And once the authorities knew where the crack was, where the volcanic eruption started, they were able to evacuate people in the vicinity. So, and then within the next few days, there was a big ash and gas plume rising up to several kilometers tall, and it was piercing through the clouds like the image I showed you earlier from the aeroplane. And this was going on then for several months. So the volcanic activity lasted for a total of about 3 months. And here we see a picture, Dia, Spanish day 1. And here is day 87 of the eruption. And within about 3 months, a big volcano grew, and it grew with about It grew about 350 meters in the 3 months, which is quite a staggering rate of about 3.5 meters per day. So this is how the volcano looks now. There was no volcano before, and you see the yellow sulfur. We come back to that later. So it still smells very badly if you go there still today, I'm told, month after the eruption. And yeah, you see the area here, the lava flows covering all that, and we'll talk a little bit more about that later on as well. So here's another image. This is a Google Earth image, and here's Google Street View. And you just see these two houses here. There's a white house each. This house is that one, and this one is that one. In fact, and yeah, Google wasn't quite updated when I went there, so you could actually see it without the volcano. And this was when I was there. Here, the volcano in full activity. And this was inside the exclusion zone. You needed a special permit from the authorities to go there. And you need some special volcano training so that you don't kill yourself next to the volcano. But this is about as close as one could actually go without being too close to be, to be harmed effectively. So now there was a large devastation. There was a large lava field that emanated from this volcano, and everything in its way was, of course, covered. So here you see several houses being covered by lava, and about 1,200 hectares of farmland and private property was destroyed by the lavas. The lava field is very thick in places, and it's up to 70 meters thick. And of course, there is very little chance of ever removing this lava, just so much. And here is the view from the northwestern edge of the lava field, and looking towards the volcano. The actual volcano is somewhere here. It's in the haze. You can't see that. That's an older volcano. It's not the one that produced the lava. And this is the lava field. It's rubbly at the top, but very massive inside. So now I'll talk a little bit more about the lavas. It was quite spectacular. There was literally rivers of lava flowing down the hill. And this was a picture from December of last year. And this is the view at night, and you can just see the rivers coming down the hillside. Sometimes the lava disappears and then it reappears. And of course, people wonder what happens there. That's mostly lava tunnels. The lava flows underground for a while, and then it resurfaces. And here is just the same position. Just a little later, you see the lava has come down, spreading out. And when there's steep surfaces, the lava will form channels. On flat surfaces, the lava will spread out thinly over wide areas. And that is very bad because that covers a lot of farmland, a lot of properties, and things like that. So here's a few impressions of the lava flow approaching houses. And there's two main types of lava. There is pahoehoe lava, as it's called in Hawaii, and there is a'a lava. Pahoehoe lava flows very easily, and a'a lava is more blocky. Most people think it's pahoehoe lava that's more dangerous. It's actually not true. It's the a'a lava, the blocky lava. It's like a bulldozer, and you cannot stop it. The runny lava flows around things. That's a little better. So here we have these a'a lava type, and this is the blocky lava, and there's virtually nothing you can do to stop it, and it takes things down when it comes. So the maximum eruption temperature of this lava was over 1,100 degrees, very hot, and a lot of pyroclastic material, meaning ash and little particles, lapilli as we call them, were emitted. And the total volume of material, the total lava volume was 190 million cubic meters. And the maximum accumulation thickness of the lava was about 70 meters, and the velocities were over 30 kilometers per hour. That's about the speed of a moped. So it's very hard to run away from it if you're in its way. You can if you're very fast, but you need to work hard. So, and now this lava was spreading out, and it was covering roads, it was covering houses, it was covering here a cemetery as well. And it came at enormous temperature, so there's nothing you can do. There's these legends that you can stop lava flows, and attempts have been made in Italy and in Iceland. Maybe you have heard that people can bring in the fire brigade to put water on it, but this will only cool the front of a lava flow. The push from behind is much stronger. There's very little you can do as long as the lava keeps pushing. Even if you cool the front, it will not stop things. People have tried to save certain places like some churches, but all of this failed, unfortunately, on La Palma. So here is, here is a little car that got caught up in the lava flow. And of course, it burns out very quickly. And intriguingly, you see the blocky nature of the lava flow here, but close to the car, it's actually more what we call pahoehoe type. It's more smooth lava. And this is actually because the lava got reheated from the burning car. So the lava was flowing a little better around the burning car. All the varnish and all the rubber burns really well. I've seen a whole number of burning cars. And there's very little left in this particular case from this vehicle. So here is lava approaching a road, and of course, many kilometers of good roads were covered, and this is a huge problem for the infrastructure there. And here, there's very little you can do. You cannot stop the lava. And I have a little video. Let's see whether this works. Might be a bit slow, but here we see the lava coming down this little road. So, and yeah, the video is a little slow. It's a lot faster on my screen. It looks better there. But in any case, so here we have the extent of the lava field. And this was during the eruption. And this is where the volcano occurred. And then it sent down several of these lobes. And they partly reached the sea as well, making these new lava deltas. The eruptions were very typically similar to the older eruptions in the area, the 1949, 1585 eruptions. But unfortunately, you see all the white dots, these are houses. It was in an area that was densely populated, which was different to the older eruption. They were in areas not that well and densely populated. So economically, this was a real disaster, unfortunately. So here is just a Google Earth image with the lava flow superimposed. You can see it. And there's two major lava deltas, this one and this one. So the island grew a little bit, but at the expense of all the devastation in this particular area of the island. And nowadays we can measure with satellites how these lava fields progress. And here's a timeline. The initial lava was the red area here, and then with time it was expanding and expanding. So we have a good record of how the lava field grew, and I'll come back to this later when we talk for a few minutes about geochemistry, because we sampled the lava on a regular basis. So, and we can see changes of the lava as it erupted during the eruption. And for geologists, that is quite useful because it tells you a lot about where the lava comes from, at depth, where the magma comes from, and what processes we have going on there below the volcano. So here is, here is just a very quick simplification of this. Here we have the initial flow from 20th of September, the first day of the eruption, really, and this is the final lava field at the end. So you can see how it grew, and over the 3 months of the eruption, it was taking out a lot of the surface of the island. So a few impressions of the lava field. This is an image from October 21, and here's the same position from December 21. You see how the lava field grew, and it took out a lot of banana plantations and properties. And the picture is taken from this area here. That's an older volcanic cone, and this was high ground, so the lava was flowing around it. And here you see that the banana plantation was partly covered with this lava, and this is the volcano in the background. So here's just a few more impressions, and the lower map here, that's the thickness map, and you see here, maybe just about here, that the yellow colors is the maximum thickness, and of course the volcanic cone is thick, but in here we have, as I said earlier, up to 70 meters of lava thickness. It's gonna take years for this to cool down. It's still hot today. So, and then while the eruption was going on, I got an email from the BBC and they wanted to come out. And so it's not yet aired, but we had the BBC with us, and then we had to be extra careful because the authorities told us the camera people have no idea about volcanoes. So we had an escort from the fire brigade that day. And so here we're sampling lava that's only a day old, and you can still see it steaming away. And we were able to get some really good samples from that. So we've taken samples all along during the eruption in shifts, basically. So I've been out there several times together with colleagues. And here we were trying to get lava from the fresh flow, and you kind of, you know, try to separate it and then you cool it down with water. And yeah, you can play lava soccer if you want, but only for so long. Your shoes are not very happy about it usually. And of course, generally you shouldn't do that. I advise you against it. But we got a fantastic sample set while being there. So here's a few more impressions, and here's a thermometer. This is a laser thermometer. It goes up to about 500 degrees, and you can just about see it's saying here 504 degrees, I think. So this was as far as the thermometer would stretch. So you can be a little bit more educated about where you take your sample, for example. And this is the methods you would use in order to get a handle on this. So a few words about the lava deltas. There is several larger lava deltas that formed. Several of the southern ones actually merged to become one big ones. And there's big questions about how the authorities will deal with these lava deltas in the future. The local farmers want them to be farmland. The tourist agents, they want them to be a volcano park. And well, we will have to see what's going to happen with them. So here's a small one, and here's a bigger one that has formed from several of these lava deltas merging. So here's a little video, and I hope it works. It shows how the lava was coming down the hillside and reaching the sea initially in September. So it's a daily progress from mid-September towards end of September. And then you see how it's growing into the sea. Now, there was big concern that there would be poisonous gases once the lava hits the sea. And of course, there is some, but it was no general problem. It wasn't too big in the end. So this is how it looks. And the beauty about it is that here you see some of these lava channels, and here you see the red hot lava coming out. You lose the red hot lava in between, which again means there's subterranean lava flow. There's lava tunnels in there. This is the edge of the island. This is the cliff, and here you see the lava. This is the older rock from the island prior to the eruption, and this is the lava delta. So here you get a sense how the lava fell down the ocean cliff and made this new land, this new lava delta here. And it's quite a good sizable chunk of land. So I'm curious to see what happens with it. And so the island is growing every 50 years or so by a little bit. And the old lava deltas from about 50 years ago, they're now hosting a lot of banana plantations. So here's just a few more impressions of the lava delta. And yeah, this is older lava deltas down here. They're all green, because, as I said, this is used for agriculture. And I think there's a good chance that even the new lava delta will become full with pineapple and bananas in the future. So I want to talk a little bit about the ash and the lapilli. Some of the areas close to the volcano were covered quite deeply in ash and lapilli. This was one of the main roads prior to the eruption, and you could barely see the road now because of all the ash that erupted. And this was one of the key problems. Here you see the chimney of a house. The house was effectively entirely covered in ash. And of course, ash is problematic. It's not like snow. Ash is very dense, and you see it here. So this is the roof of a house, and the ash is very heavy. And that means roofs tend to collapse under the weight. So this is a real problem. So people had to go in repeatedly and dig out the houses so that the ash would not be too thick, because otherwise the structural instabilities would be too strong. So, and here is just some impressions of a little shed close to the volcano, and you see the thickness of the ash here. And indeed, part of this roof had already collapsed when I was there at the time. So the ash is brought up in eruption plumes, as we call it, and these can be several kilometers high. And you see here, there's the volcano, and this is the ash plume, and it's dragged down, in this case, to the south. And actually, some particles and gases were brought all the way to Central America, or here from La Palma up into Europe. And you can measure that there's elevated sulfur contents in the air, elevated particle contents in the air from these eruptions. And as I said, you have to dig these houses out because otherwise they collapse. And just down here, you see in the lower left, there was some people. Now, this video is actually coming with sound, but the sound didn't work earlier. So this was just the roof of the car. And you could actually, if you hear the sound, you could hear it clinking. It's the ash falling down. It's clickety, 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 click. So unfortunately, you can't hear it now, but this gives you a sense of how ash fall actually is. And all these little dark specks on the screen of the car, that's little ash particles. So, and here is the here's the soccer ground of Las Manchas, and you can see the goalposts halfway covered in ash. The street sign is covered in ash, so it's really thick layers of ash, and this will take quite some time for it to be fully removed again. And here is a little section that we dug in order to sample the ash. So this is quite thick, meters thick, literally. Now, I should point out, ash is actually very dangerous if you inhale the ash, because here's a little ash particle, and you see it's got these tiny little spines. What happens is that there's gas that expands inside the volcano. It's a bit like soda water. If you open it, the gas bubbles expand and they cause the material to shred. And this happens in magma as well. And this is how ash is actually made. It's shredded lava from expansion of the gas bubbles. And you see the gas bubbles here. This is the outline of one bubble here, and here's another bubble, and it creates these thin films that then rupture, and these create tiny spines, and this is spines of glass. And if you inhale them, they get stuck in your lungs. You can't get them out anymore. So this was a huge problem, and if the particle density in the air is too high, then you really have to evacuate the people, and you have to lock people inside, because inhaling the ash is really dangerous. Not immediately, but in the long run, because the particles will accumulate in your breathing, in your respiratory system. So another feature that we found, and this is one of the reasons why I'm also here, because one of the local volcano team members has found some of this material in some of the Saudi Arabian volcanics as well. We call them xeno-pumice. These are strange things that came up during the eruption for some time, for some weeks, and it's white, frothy material all amongst the dark volcanic material, and they have caused people to be quite puzzled. And this material turns out to be material ripped from the underground, brought up by the volcano, and it's heated and it's frothing up. It becomes like a foam, and of course now it's solid, but there was these white things amongst the dark volcanic material, very intriguing. And these foreign pumices, they are an interesting window into what happens under the volcano. So I'll talk a little bit more about them later. And here we actually found some rather big ones. And these are foreign materials that the volcano brings up. It's a great source of information of what's going on under the volcano and inside the volcano. So here we also have these large soccer balls of material, hot material falling down from the volcano and then rolling down the hills. This is quite a dangerous phenomenon. And here you see the size of some of them. So, and they are red hot inside. So this is material that was thrown out of the volcano and then it was rolling down the hillside at enormous speed. I was really quite surprised. And I have a little video here. Let's see whether we can make it work, but it might be a bit too slow as well. So, but you can just about see there's one of these guys rolling down the hillside here. So imagine it's coming towards you. And then it came to rest. And so we had a chance to look at it. And we took a sample as well. So fantastic material. And well, the safety rules for volcanologists is you don't run away from these things. You actually have to stand there like a goalkeeper in soccer and you have to move away from it when it comes, because if you run away and it comes after you, you don't see it. So your chance of being hit is actually even bigger if you turn around. So you have to stand your ground and have it come towards you and then you step aside. So here's the thing. And we also opened it. Let's see, I hope the video works. And here we see the glowing interior of it. The outer crust was a bit cooled, but the interior was still hot. And there you can actually kind of really see lava cooling down in a live fashion. So now a few words about the craters. And there was up to 7 craters forming on top of the volcano. And here we have some craters by night. There was fire fountains coming out, very spectacular actually, and different craters active at different times, sometimes also simultaneously. So here you have an upper and a lower crater being active together. And this made for really magnificent footage of how volcanoes work. Here you see the main crater being active, one of the side craters being active, and there's another crater here a little bit off that opened up on the flank of the volcano. And here you see me posing in front of the volcano with several craters being active behind it. So rather fascinating to see this live, I have to admit. So this is some images. This is the craters now after the eruption. And I hiked there a few weeks ago, and it's like a, well, it's like a battleground. There's only a few tree trunks left, but there's no leaves on it. And here is the sulfurous area of the crater. And this is how it looks from a distance. So, and when I was hiking up there, I took some samples. Hopefully we can analyze them in the lab. They're currently in Stockholm in the lab for chemical and isotope analysis. But you see the little sulfurous bits there. These are the shapes of droplets. So this is actually sulfurous magma. So liquid sulfur that has solidified. So it must have been several hundred degrees hot when this was solidifying in this particular shape. And this has formed inside the crater area, but not much beyond. So a few words about the earthquakes now, for those of you who are interested in that, the seismic information. So what happened during the eruption is we had intensity changes. So there was initially earthquake activity quite strong, and then the eruption started here. This is a timeline of the eruption, and then it was going up and down a little bit, and up again and down again and up again and down and up and several times. And it was actually really frustrating for the population because the people thought, oh, it's getting weaker, and then it got stronger again. Oh, it's getting weaker, and then it gets stronger again. And this is a real problem, and I think we have to do a bit more research on that, why this is happening. And I have some idea, I'll mention it later. But here we have the earthquake depth, and this is longitude and latitude. And there seems to be some major area of earthquakes here at about 10 to 15 kilometers depth, and about another one at 35 to 45 kilometers depth. And we have to assume this is where the magma was sitting prior to the eruption. likely in two levels, in two magma chambers or reservoirs. And I suspect this is the reason why things are going up and down, because if you have two systems connecting and they're feeding into each other, it probably causes a bit of a jam every now and then. And this is my hypothesis, at least. So, and here you see the timeline, the date down here, and you see the earthquakes. This was just before the eruption. The eruption started here, September 19th. So this is earthquakes of the magma rising up to the surface. But during the eruption, there was earthquakes in this level, this upper level, and in a deeper level here. So again, picking out two main areas where things must have been moving, and presumably this is the reservoirs where the magma was stored and withdrawn from. So, and yes, this is the size of the magma chamber or the reservoirs. We get an idea here. The lower diagram is again the up and down. And my suspicion is that the interaction between these two reservoirs, that's what's causing the ups and downs. But we have to do a little bit more work to see whether this is actually true. So here is the intensity of the earthquakes. This is the earthquake magnitude. And here we're reaching up to about magnitude 5. That's serious shaking, magnitude 5. So things are falling off the shelves at that. And the strongest earthquakes were actually in the deeper reservoir. So the deeper reservoir was feeding towards the end. And towards the end of the eruption, the deeper reservoir was the main contributing reservoir. And we'll see that also in the chemistry. I come back to this just in a minute. For the people who are interested in rocks and geochemistry, I'll spend a few minutes on that as well. So this is the geochemical part now, and you can take rocks and put them under a microscope, and then you see little crystals there. And if you change the light, if you polarize the light, the crystals come, they're depending on their chemistry in different colors, which helps the geoscientists to work out what crystals we're actually looking at. And early in the eruption, we had just a few tiny little crystals. There are beige colored and pink guys here. But towards the end, the crystals were getting bigger and bigger and larger. So this was a very important observation. It tells us that we were taking magma from deeper and deeper within the system. And this was a useful thing to realize. And we also had these strange white things, the xeno-pumices, as I mentioned them earlier. And here's just a few images from the microscope. And also with the electron microscope, we have different mineral types. At the beginning, we had a mineral called amphibole that has a bit of water in it. Towards the end of the eruption, we had no amphibole anymore. And amphibole grows usually at about, the level just under the volcano. And towards the end of the eruption, when the deeper reservoir, the deeper magma chamber was contributing more strongly, we didn't have that mineral anymore. We had mainly another mineral called olivine. And this is the olivine here. Here's an example of this chap here. And this tells us that likely we were sucking magma from deeper and deeper within the system under the volcano. And at some point, the magma was exhausted and the eruption stopped. So this also gives us a hint to better understand how long these eruptions will actually go on. There's a limit to them, because during the eruption, people got really frustrated, saying, when will it end? When will it stop? And nobody had an idea, but this actually tells us something. I think we can monitor the minerals, and this will help us in future to say something about when things are drawing to an end. So here's some useful things for the future. So for those of you who are into geochemistry, this is just the classification plot. And here we have silica against total alkalis. This is older eruptions in the area, 1971, 1949, etc. And this is the eruption that we had in 21. It spans quite a spectrum, more than the previous eruptions. We had these white guys, I mentioned them, these xeno-pumices. They're completely off. They have nothing to do with the volcano itself. They are clearly not related to the volcano directly, and they are older sedimentary rocks, likely from the ocean crust, that were brought up accidentally. But that is actually good for the geoscientists, because it means you can look at the ocean crust without having to drill a hole. The volcano has helped us to look at some of these rocks. It brought them up for us. So, and here we have the rock chemistry over time, and we don't have to go into details, but here we see the dates for the rocks. Here's the individual dates on the right-hand side, and we can see that with continuing eruption, the chemistry was changing. The aluminium content was going down, the magnesium content was going up, and magnesium is a good sign for deeper, more primitive, as we call it. And indeed, this is consistent with the lower part of the reservoir system contributing more and more during the eruption. So here we have good indications of how magma is sucked into the volcanic vent with time over the 3 months of such an eruption. And here we see different chemical parameters changing with time. Here's magnesium. It's rising up during the first few days of the eruption, and then it stays constant. Aluminium is going down, and then it stays constant. And here we have calcium rising up almost consistently. Total alkalis going down and then staying rather constant. And this is very informative for us, because I think what we're seeing is that this initial part is magma from the upper reservoir, the 10-kilometer reservoir, and then we're drawing magma more and more from the deeper 35 to 40-kilometer reservoir. And here we got the first isotope results. They're fresh from the lab, and here we have oxygen isotopes. There's a lot of oxygen in rock, so this is very useful. And normal Atlantic Ocean crust is about following this line here, but what we see here is there's a bit of wobble, and then we are hovering around this line. So this is very interesting. It coincides with this change here. And I said my hypothesis is that this comes from this upper reservoir at about 10 to 15 kilometers. And well, in order to explain this wobble here, we have to look a little bit further. So here's some work I did many years ago about how the ocean crust actually has oxygen distributions. And what we see is there's some low oxygen data and there's some high oxygen data at different levels in the ocean crust. And here we have a distribution on the left-hand side here where we're going down and up at the same time. So it would imply that our reservoir was sampling this material. It would have sat right in the ocean crust at this boundary between the low and the high ocean crust material. And I think we're on to a winner here, because this is previous work from a guy called Klügel, and he measured the ocean crust under the island lying at about spot on 10 kilometers. And this is the seismics again, and it's a bit small, but this is the 10-kilometer range. So the seismics is consistent in the geochemistry as well. The first 10 days of the eruption was drawing magma from the upper reservoir, and then we must have drawn magma from the deeper reservoir. So this gives us a great understanding of how these volcanoes are fed. This will be extremely helpful for future eruptions in the area. So this is the model, therefore. We're starting off bringing magma up from this upper reservoir, and then increasingly we are tapping more magma from depth. This would explain the distribution of the earthquakes as well as the geochemistry. So I'm going to spend the last part of the presentation with a little summary of the not so good parts of the eruption. That was the last part was the scientifically exciting one, I'd like to think. But now we have to also spend a little bit of time with the damage, because these eruptions, while they're scientifically very, very informative, they of course cause a lot of trouble. So the eruption lasted for 85 days. And can you imagine if you're evacuated from your home for several months, having to live in a shelter, not having an income? It's quite a disaster. Almost 8,000 people were evacuated. More than 2,800 buildings were destroyed. This includes 1,300 homes and about 1,500 utility buildings. Almost 1,000 hectares of plantation land were destroyed, either covered by lava or pyroclastic material. Then I say 70 kilometers here, but the latest news I got was actually closer to 100 kilometers of vital connecting roads were capped. And there was one big road, LP2, which was connecting the southern part of the island here with the northern part on this western side of the ridge. And it was cut, of course, meaning you couldn't drive anymore to the northern part of the island. On that side of the island, you have to drive all the way around, adding hours to your journey. From an infrastructure point of view, a complete disaster. Now, luckily, nobody actually directly died, which is a real achievement, but the financial loss is on the order of about 1,000 million euros. So for the European Union, this is a real disaster, and it's now tapping into the emergency funds of Spain, as well as many other countries, trying to fix what can be fixed at this stage.